So with all that working out we did in the last video, we pretty much covered what's on page 16. Just maybe one thing to show you is first of all a definition, just to highlight it. An orbital we talked about as what sublevels are made up of, is a region within an atom that can hold up to 2 electrons with opposite spins. At the time I kind of skipped the idea of opposite spins just to kind of build on that now. Basically what that means is it's the reason that you can have 2 electrons in the same space. Because if I've got an orbital, and one orbital could be like a sphere, and that's actually what an s orbital looks like, it can hold up to 2 electrons and they're whizzing around. If you stop thinking about it though, that's not particularly favourable for electrons to be close to each other in the same space, because they got the same charge, they're both negative, and things with the same charge like to repel each other. That's true unless they've got what we call opposite spins. Spin is kind of like a strange quantity. It's a little bit like charge but not charge. It's kind of only for things which are really small. The rule is if you've got opposite spins and spins either up or down, so this electron might be spin up and this electron might be spin down. If they've got opposite spins, they're not too repulsive, they're not actually too polar being beside each other, even though they got the same charge. So that's where that wee bit of the definition comes in. They can hold up to 2 electrons as long as the electrons have got opposite spins, which means they don't repel each other as much. The only other thing maybe to show you might make things a bit clearer, we've got a slightly clearer diagram of how the sublevels are laid out for each shell. So that's kind of our GCSE model where we have like wee rings going around the centre. We've updated it now. We've still got layers, but they're not like uniform layers, they're made up of sublevels. So the first shell has got 1 sublevel, second shell's got 2, third one's got 3 and 4, and the fourth one. And you see the different names of those sublevels. So you've got the 1s, 2s, 3s, 4s, the first one for each energy level, then the P, then the D, then the F. As you see, they're of increasing energy, so you'd fill up the first energy level first, then the second, then the third, then the fourth. The one thing you need to be aware of is the fact that this diagram is actually better on page 17. The sublevels aren't of the same energy. So in other words, the 2s will be filled before the 2p because it's slightly lower, the 3s filled before the 3p, and etc. So it's not like a flat diagram like this one's maybe making out to be. There is an order to how you fill up the sublevels as well, based on their energy level, but we'll get to filling them up in a second. Top of the next page, you're probably wondering as well, with diagrams, like what does it actually look like? It gets a wee bit complicated. You actually can't draw proper diagrams for atoms because they look horrendously complicated with all the orbitals having different shapes. All you need to know is kind of the shapes of the first 2 simplest orbitals you can have. So we talked about the fact that s sublevels are made up of an s orbital, and we talked about the idea that p subshells are made up of 3 p orbitals. The s orbital actually is a spherical shape, so it looks like a ball, and you have 2 electrons filling inside there. So that's something you could be asked to draw in an exam. The question would just say, draw an s orbital, just draw a circle. P orbitals are dumbbell shaped, they're kind of like figure of 8 shapes, so you just draw like that in the exam. So remember, in the P sublevel there's 3 P orbitals. The reason they're different is they kind of lie along different axes, so they're kind of all pointing in different directions. So we're showing one here, the second one would kind of sit along that axis, the third one would kind of sit along that axis, and they would all contain up to 2 electrons each. This is all on top of the s orbital, so you'd have this shape on top of that shape on top of that shape. So hopefully maybe get the idea now why it gets very complicated to draw pictures of atoms like we did in GCSE. The shapes come a wee bit too tricky to kind of see through. So we're not going to have to draw D or F orbitals, just S and P. S are sphere shapes and P are dumbbell or like figure of 8 shapes. So now we get on to looking at how we actually put electrons into our orbitals. There is very fancy scientific rules that explain why or how you fill up electrons. I'm not actually going to worry about them too much now. You can read them yourself, it's quite interesting the way they're worded. We don't have to like learn them off or recite them, we just need to apply them. And I'm just going to go straight to the actual application of them by looking at some examples. So first thing to look at is the graphs down here, which reveal to us the order that we fill up our sublevels. And the first rule is, which actually what the Aufbau principle is that you should put electrons into the lowest energy level that's free that you can. So in other words, if you've got no electrons filled up yet, you're going to put your first one in the 1s orbital. It's going to be filled up once you put 2 in, because remember the s sublevel holds 2 electrons. Then go up to 2s. Once it's filled, you go up to 2p. Once you fill it, it's going to go up to 3s, then 3p. Now here's where we get to a little issue. The reason that in GCSE you thought that the third energy level holds up to 8 electrons when in reality it can hold up to 18 is that once you filled up the 3p, so you got 2 plus 6, that'll be 8 electrons in the third shell. Look at the diagram here. Just because you got so many sublevels in the 4s, what you might notice is that the 4s sublevel actually ends up being slightly lower energy than the 3d sublevel. So the next sublevel you actually fill up, because it's lower energy, will be 4s. You put 2 electrons in there. Once that's filled up, you then will fill up the 3d and put up to 10 electrons there. Then you go back to the 4p. So it sounds like really random, really crazy, but there is a reason for it. It's just that because we get very crowded with energy levels, it just so happens that the highest 3 sublevel ends up being higher than the lowest 4 sublevel. So we fill up the 4 first. Now, there's a couple of diagrams you can use to kind of work out the filling order. You can use things like this. So you write down them all kind of as a list. So 1s, 2s, 3s, 2p, 3d, etc. And if you use kind of left diagonal arrows, that gives you the correct filling order. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, etc. So I can help you work that as well, but you will kind of pick it up instinctively out of habit. So with that kind of setting the scene, I think you're only going to be happy here if you actually have a go at seeing like how this actually works in practice. So this is called showing the electron configuration. It's exactly the same as what you're asked to do in GCSE, where you're asked to put electrons in the shells. We're just doing with our new sublevels and orbital system here. There's actually 2 ways of showing that configuration. We're going to look at the first one first, then we'll leave the second one till after. This one's called Spd Notation. What basically means is that you write down in a little list how the electrons fit into the orbitals. So let's take an example. The first one here is sodium, so I'll do it kind of bigger up here. What I would do is, just like I did before, I look at sodium, I look at its atomic number in the periodic table to find out how many electrons it's got, and I find that sodium has got 11 electrons. My task now, if I'm trying to do Spd notation, is to write which electrons will fit into which orbital. So I go in the correct order of filling. So the first orbital I fill up is 1s, so I write down 1s. It can hold up to 2, and that's obviously going to be filled because it's got 11 electrons put in. So I put a wee 2 kind of superscript. It's like a wee small 2 up there, a bit like squared, but we say 1s2. Then I get into my next sublevel, which is a 2s. It can also hold 2, so I've now put 4 electrons in. I now get to my 2p sublevel. It can hold up to 6, and that'll be 2 plus 2 plus 6, which is actually 10. So I've still got 1 left over. And that 1 leftover electron will be going into my 3s, so I end up with 3s1. So if I was reading that out, I would just say the electron configuration of sodium is 1s2, 2s2, 2p6, 3s1, where the numbers are showing the number of electrons in each individual sublevel. If we look at another example quickly, I know it's already written out, but let's just do it to be complete. So if I look at chlorine now, if I look at the periodic table, I know that chlorine has got 17 electrons. Let's try and put them in. So first one's going to go in 1s and it fits 2. Then 2s can hold up to 2. 2p can hold up to 6. 3s can hold up to 2. Let's just keep track how many we've got. 2 plus 2 plus 6 is 10 plus 2 is 12, so we can get a few more in. So we've got 5 left over. So my 3p can hold up to 6, but I'm only going to actually use 5 of those electrons. And that gets me my configuration for chlorine. So it's the same idea. You're just putting electrons into the shells from lowest energy up to highest energy, but just putting in individual sublevels now. And you stop once you've run out of electrons to put into the shells. So just as a little check, just midway through this video, let's just see if you can do phosphorus, just if you pause the video. So phosphorus has got 15 electrons, so pause it quickly and see if you can fit them in the same way we did here. So hopefully you've had a go at that. So how that fits in is 1s2, 2s2, 2p6, 3s2, so let's check that, 2, 4, 10, 12, got 3 left, 3p3. So to apply that system, just you have to know the correct order of the orbitals and sublevels. Now, there's a couple of places where I can get a little bit trickier, not too much, just a couple of areas you can trip up in. First one is in transition metals, because transition metals, as most students say, involve the d orbitals, specifically the 3d. And remember we looked back on the previous page, the idea that when you've got things involving 3d and 4s, it gets a bit complicated because the 4s fills up before the 3d. So if I look at something like titanium, in fact we'll use a different bit of paper. So titanium, if I look in the periodic table, it's got 22 electrons. So the challenge is no different. I'm going to put them in the correct order. So I'll start that. I do 1s2, 2s2, 2p6, 3s2, and then 3p6. Let's keep track. 2, 4, and 10, 12, 12 plus 4 is 16, so I've got a few more to put in. So have to be careful here. My next one's going to be filled up is the 4s because it's lower energy than 3d, so it fills up to 2. And then I've got 2 left to put in, so in fact let's check, did I count that up right? So 2, 4, 6 is 10, 10 plus 2 is 12, 12 plus 4 is, 12 plus 6 is 18, 18 plus 2 is 20, and then we've got 2 more to put in, so I'll go into the 3d2. Now, apart from remembering that the 4s is filled up before the 3d, that's fair enough. The one annoying thing you have to remember for the exam, whilst you have to remember that the 4s is filled up before the 3d, what your exam board likes to write, because it's kind of like a chemical convention or rule, even though you filled up in that order, you should write your final answer in numerical order. Why maybe that is all your 3 levels should come before the 4 level. So that's your working out. What you should finally write there is 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, 4s2. Even though the 4s is filled up first, you should write after the 3d, just to keep the numbers in the correct order. Just have to try and remember that. Next little complication. 2 of the transition metals have anomalous electronic structures, which we'll get into the why of that in a little second, but just need to kind of flag it up for now. If you worked out chromium, just according to the same rules we looked at before, you end up with this configuration. You'd end up with, just ignoring the start, just the end, 3d4 4s2, and if you did copper, you end up with 3d9 4s2. In reality, you don't get 3d4 4s2, you get 3d5 4s1, and you get 3d10 4s1. In other words, what chromium and copper do is they take an electron from the 4s and move it into the 3d compared to what you expect you should get. The reason they do that is something we'll look at later on this topic, is that half-filled subshells, similar to fully filled subshells like full outer shells we did at GCSE, are stable. So if we look at the expected one for the 3d orbital, 3d4 isn't half filled, remember D holds up to 10, so 4 is very close. However, if it takes one out of the 4s and puts it into the 3d, that will get 3d5, which is half filled and quite stable. 4s is also half filled now, so that's still quite stable as well. 3d9 is very close to being a fully completed subshell, which will be quite stable. So if it takes one out of the 4s, it gets 3d10, which is now fully complete and quite stable. 4s is half filled, so that's not too bad at all. So these 2 elements, and these are the only ones you have to know about, they stand out as anomalies. They adjust their configurations to make it more stable for themselves by getting either half-filled or fully filled 3D orbitals. So you just have to remember them, they don't follow the pattern. Some people like to, when they get into the exam, open up the periodic table and put a mark beside copper and chromium in case they forget them. So it's important that you know that there are exceptions to the rule. Finally, the last rule to look at, just to kind of go through the whole kind of picture, is about making ions. So if you're asked to take electrons out of atoms, you just do it the same way as before. So if I had sodium looking like this, if I wanted the sodium plus electron configuration, that's taking electron out. So I just go down to 1s2, 2s2, 2p6, 3s1's been taken out. That's now a full sublevel, a bit like a full outer shell GCSE, so that's quite stable. Just take electrons out. One problem just with transition metals is flagged up down here. Transition metals lose the 4s electrons before the 3d electrons. Now that goes to the opposite pattern pretty much of what you expect, so I'll just emphasize that again. Remember, when you're filling up transition metals, you put electrons into the 4s first before the 3d. So you'd expect maybe to take them out of the 3d first because at this higher energy level. Fortunately, the picture kind of changes once you're taking electrons out. So whilst you put electrons into the 4s first, you also take electrons out of the 4s first. So just always remember, you put in 4s first, you take out 4s first. Always do your changes to 4s before you do the 3ds. So I know I've gone through that quite quickly, but I don't want to make the video too long and cumbersome. It just takes a wee bit of practice. Here's a little table allowing you to do some practice here, which kind of covers lots of stuff we've done in this topic so far. You've got 5 species here. Some of them are neutral atoms, some of them, well, most of them actually are ions. The left-hand side is just kind of what we did at the start of the booklet. So working out atomic number, mass number, protons, electrons, neutrons. That's just some periodic table work. Then I want you, with the number of electrons, see if you can work out what the electronic structure is for each of these species. So pause the video, or you can watch the first example I go through just to see, and then see if we get this correct. So go through the first one, just in case you need that wee kind of helping hand. So magnesium, if you look up in the periodic table, it's got atomic number 12, mass number 24. That means it's got 12 protons, 12 electrons, assuming it's neutral, which it is, there's no charge there, and 12 neutrons. Important thing to look at is the number of electrons for electron configuration. So what I'll do there is I will do 1s2, 2s2, 2p6, 3s2, and that should add up to 12, which it does. So that's the electron configuration for magnesium done. So if we go at the rest in there and see how you get on. So hopefully that's what you got. Probably the one that stands out just to check is the last one, nickel 2+, because you're moving 2 electrons from it. Just a thing to remember from what we just talked about just before this. When you're taking electrons out, always take out of the 4s before you take out the 3d. So in this case, it loses its 4s2 electrons and keeps the 3d8 electrons. One final little trick to look at in this little section, another way you can just write that structure, because as you can see it gets quite long when you get with the later on elements. There's a little shorthand you can use which makes use of the noble gases, because noble gases have full outer shells. So for example, argon here has got 1s2, 2s2, 2p6, 3s2, 3p6. You can use that as a reference point. So for example, if I was looking at potassium, so like potassium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, so I'm already getting bored already, it's very long. What I can do is I can take that reference point of argon, which covers most of potassium's electron configuration, put it in square brackets, and all I write afterwards is what's left over. So after I got the argon configuration, I just got a 4s1. So applying that to maybe one of the other ones, magnesium, it's close, it's just after neon in the periodic table, which would end in 2p6. So I can write that as neon square brackets and 3s2. So it's not a necessity to do that. You might see it kind of in questions. I don't think they'd ever really ask you to do it by force, but you might see that as you go through the course, just be aware of it. So I said that's one way of showing the electron configuration. It's probably the most common. There's a second one which isn't too complicated in the back. That's kind of the same idea again. It's just a more diagram-based form of showing the electrons. Gives you a better idea what's going on. It's called Electron the Box Notation. And what we do here, instead of just giving like code like 1s2, 2s2, 2p6, we draw a box to represent each orbital of each sublevel. So remember, the 1s sublevel has got 1 orbital, 2s is 1 orbital, 2p holds up to 6 electrons, which requires 3 orbitals. So we give each one in the box and we show electrons fitting into those boxes with arrows. So I know we've got an example here, but I'll show you maybe a slightly different one. So if I had, let's go for sodium again, it's the first one we looked at. It's got 11 electrons. So we looked at in the previous page, if you give the Spd notation, which is the more common one, you end up with 1s2, 2s2, 2p6, 3s1. If I was doing electron and box notations, I'm going to draw out all those sublevels as boxes. So 1s comes first, then 2s has got 1 orbital, 2p has got 3 orbitals. I can do like a long box and divide it into 3, and then 3s got 1 orbital. In the diagram on the right, you've got kind of full arrows. What you might actually see is like half arrows to show the electrons. So here's the important thing. I need to put 2 electrons in at 1s. They must have opposite spins. The direction of the arrow shows you the direction of the spin. So I have one going up and one going down. That's the 1s filled up. Seeing the 2s, one going up, one going down. Now, the 2p is important to kind of fill it the correct order. Even though we're going to fill it completely and show you the correct order to put it in. So, first electron goes here. Now we invoke what we call the sitting on the bus rule. The idea is that if you get onto a bus and you see lots of people who are sat in double seaters by themselves, you'll try to find your own individual seat before you sit beside one of them. Same with electrons. So the second electron doesn't want to sit beside this electron for now unless it has to, so it gets a new seat for itself. The third electron will do the same. The fourth electron's kind of not got that option anymore. It has to sit beside one of the other electrons. So it goes back to the first one, but goes to spin down, and so on to fill up the rest. So you never put 2 in first. You go 1, 1, 1, and then pair them off afterwards. 3s just got 1 electron, so we'll put spin up there. So it's a bit more of a visual form of showing how the electrons fit in. It also shows you what specific orbitals they're fitted into, which was a wee bit of advantage as well. So on the back of that, see if you can do this exercise here to finish off with. Nitrogen, oxygen, and copper. Electron the Box Notation for those three elements. You just look at the periodic table, look at the number of electrons each one of them's got, and see if you can fit them in the correct boxes. So hopefully this is what you got. Again, sorry for my scrawly handwriting. So in nitrogen, you should end up with 4 in a 2p. So remember, you fill them up singly first and put the fourth one in with that first box. Oxygen, you got one extra one, so you get a fifth one here. Copper, quite a big one. You probably wouldn't get that in an exam. But you're filling all the way up to 3D. Probably would put 4s lower energy than 3D in this case. Remember, it's the anomaly. It's got 4s1 because I want to get a full 3D sub-level. So it ends up having 10 in that 3D level there.